Yes, now that we've spent 17 minutes just talking. Yeah, I mean, hey, yeah, it's still education. All right, for those of you just joining us, watching this recording online, we spent the last 15 minutes talking about Jeeps, speeding infractions, and credit scores. I'll have you know that I've only ever gotten 2 speeding tickets in my life, and the last one is 7 years ago.
Well, actually, that's pretty good.
Mm-hmm.
Congratulations on that.
You know, I
Thank
think
you.
she's becoming a true Texan driver. Who knows, honestly.
Yeah,
Especially here in Odessa.
you don't slow down for the yellow, you blow through the yellow, right? This is the Texan way.
It's just me who follows the rules.
You don't, when you're turning left through an intersection, you always go into the lane you want to, not the lane that you're supposed to be in.
Right.
Yeah, this is the Texan way.
And how can we...
I don't know, it's just,
So dumb.
I've never seen anyone else drive like that but Texas.
I do that. You guys should drive somewhere else.
Oh, what?
Because you guys don't follow the rules, that's why.
It's crazy. It's because they do it too.
Yeah.
Maybe if you guys would follow the rules, there wouldn't be so many accidents.
You guys.
Hey, I've only been in one and it was the other lady's fault.
Yeah.
Okay, that's pretty good.
Okay. All right. So, any questions for me before we get started? Any questions about what we discussed on Tuesday? I just realized, so for those of you watching this recording, I have been sick for the last day and a half. Finally started feeling better about 1:30 this morning, so I'm pretty low energy. So I'm going to be sitting down and taking it nice and chill today. I apologize, I won't be able to keep that energy up. Please try and stay awake.
You're just talking to yourself,
Yeah, okay.
though.
Okay.
It's okay, Josh. I'll
Thank you. Okay. So we talked about igneous rocks and intrusive activity last time. So igneous rocks made through the crystallization of magma and lava. Intrusive activity being the bodies of this magma that rise up close to the surface and then do any number of things, right? They could just sit there and crystallize, they could form volcanoes, that sort of thing. So that's what we're going to talk about today, is what happens when that material breaches the surface and creates what we call a volcanic eruption. Okay? Naomi, would you grab the door for me? Thank you. Who's coming? Oh, hey, would you grab the door for me on your way in? Thank you.
It's still locked, by the way.
It's what?
It's still locked.
That's fine. Technically, it's always supposed to be locked as long as I have high schoolers in the classroom. Yeah, freaking minors. Yes, keeping my door locked would work very well in my classroom with windows for walls.
They'll never get in.
They'll never see us. All right. All right, so let's talk about volcanoes. So this is Mount St. Helens. Some of you may have heard about this before. Mount St. Helens erupted in 1980, a little bit before your time. Heck, way before my time, right? Way. Yes, I was born in 93. Thank you very much.
No, I think it was around your time.
Yeah, sure.
For us, it was a little bit before our time, and for you, it was way before your time.
Yes.
Okay.
Yes.
It's okay.
That's how it works. That's how it works.
Checking them out.
Just go with it.
I know you were there when the founding fathers signed the Declaration of Independence.
Oh, girl, I wish. I wish. Okay, so you can see from this before and after picture here, there are some things that are different, right? When this volcano exploded, it took 400 meters of its total elevation with it. Think about how much rock that is in a mountain that tall, right? Blasted that outward. The ash cloud went 18 kilometers, not out, up. 18 kilometers high and dropped ash all over the United States. As a matter of fact, this is a container of Mount St. Helens ash that someone collected right here in Odessa.
Can I sniff it?
Sniff it? No, do not even open it.
Can I do a line on
Should I be concerned that your first instinct was to sniff the mysterious powder?
You gotta use the scientific word.
Exactly. I'm doing
Ah, yes. Clearly Mount St. Helens. 1980. What a wonderful year. All right, so
exactly like
so this ash cloud dropped ash as far as Oklahoma. Definitely dropped it here, which is why that was able to get collected here. The eruption that caused that much damage to this volcano was equivalent in energy to exploding 1,600 nuclear bombs at the same time. Yeah, pretty intense. Now, when a volcano is getting ready to erupt, so we do everything we can. I'm using the royal we here, geologists in general. We do everything we can to try and monitor these to make sure that. Oh man, there's another sneeze coming.
Bless you.
Can't pre-bless someone.
Yeah, you did. It's
Y'all.
not sneeze. I bless you, not sneeze. See? You didn't sneeze.
See, even
Yeah, see, I do when I do that, I just say pineapple.
pineapple.
Yeah, when my wife is about to sneeze, I say pineapple, and then
Sick purple elephant.
most of the I mean, it really doesn't matter. What it does is it takes their mind off of the sneeze, and then they forget to sneeze.
Oh, see, like we just did to you.
Yes, exactly. But it doesn't. Okay,
I
whatever,
bless it.
whatever,
Bless
whatever,
you,
whatever.
not sneezing.
So this volcano was under observation for a while. They had some indicators that it was probably going to erupt at some point soon. The USGS, that's the U.S. Geological Survey, they are the agency that is specifically dedicated to watching to make sure that threats to the American public that are natural in origin are watched over. Okay, now when I say threat, I don't just mean like volcanic eruption. They test water quality, right? They watch for landslides, soil testing to make sure that there isn't a buildup of salts or phosphates or things like that. Okay, so the USGS covers a lot of land there. Pardon the pun. But they were watching this. They actually sent a guy, Frank Johnson, I believe is his name. They sent one of their geologists to watch this volcano, to watch Mount St. Helens. And he set up camp and he was watching it. And in the last 24 hours before Mount St. Helens erupted, it bulged outward 6 feet. Like, what was happening there? For it to be bulging outward yeah, and it's filling up with magma. So the inside is filling with magma, getting ready to pop, and then it did pop. It erupted. Now, there was something very atypical about this eruption. Most volcanoes erupt out the top. From looking at the after picture here, can you tell me what was different about this? Yeah, it erupted out the side, the northern side, okay, that northern flank. This is not normal. It was not expected. And unfortunately, our geologist had pitched his campsite on this hill right here. Oh yeah, he died. So 58 local people and one USGS geologist were killed in this eruption. The last thing anyone heard from him was a message, control, control, it's happening. And then that was it. Because the eruption immediately. Yes, when I die, I want to be thrown into an active volcano.
Okay, Josh, I'll remember that. So when your wife questions why
Why do you have my husband in a helicopter? Oh, it's time. It's his time to go.
it's his time to go, you know,
Yes.
he's 80.
He gave one too many dad jokes, and we decided it was it. Okay, so yeah, it erupted out the side and killed a bunch of people. Now, why were there people around for it to kill? Well, here's the question, and you actually have a discussion board that's that touches on this subject later on in the course. When you know that there's going to be some kind of a natural disaster, like an earthquake or a volcanic eruption, the government warns the people, but cannot compel them to leave. So these were the people that decided to stay, though there was warning given. And here's kind of a moral question. Should governments be allowed to compel you to leave? Should they have that ability to compel you to leave? Yeah, to force you to leave your home.
I mean, there's enough of us. There's plenty of people here. They're okay.
I mean, if it's not natural disaster,
Wow.
they're just doing it, then no. But
What
I mean,
that is natural selection.
honestly, something like that, yeah.
That is curiosity. can lead a horse to water, but you can't make it drink, that kind of stuff. That's natural selection.
She's got a good point. I agree.
Thank you.
Wow. Wow.
My mind in 2.5 seconds.
It's an interesting point. I mean, so you're what you're saying is if essentially if they're too dumb to go, then they die.
Yes.
Yeah.
Survival instinct.
Got it. Okay. All right. Any other thoughts on the matter? All right. Something to think about over the next little bit until you get that discussion board, but it is a subject that comes back up.
I'm just gonna put what I said in class.
Yeah, sure.
No, like actually type out what I said in class.
Sure. What I said in class, you need a little more than that, but yeah. Okay. So that's Mount St. Helens. This is Mount Tambora. This is what we call a supervolcano. You ever heard the term supervolcano?
Yes.
Usually in context to what?
Science classes.
Right, but is there a particular volcano they talk about? Yellowstone. Normally when we talk about Yellowstone, not the show. Normally when we talk about supervolcanoes, people think Yellowstone, and we will talk about Yellowstone today. There are only 2 supervolcanoes on our planet right now that are active. There are actually 26 of them scattered across our planet, but only 2 of them are active. Yellowstone being one of them here in North America, the other one being Mount Tambora here in Indonesia. The last time this one erupted was 1815, and its eruption put ash clouds across the planet. This 1815 eruption put ash clouds so far that it blocked out the sun and killed crops in New York State from Indonesia. This thing did that. So very, very, very powerful, very wide-reaching effects from supervolcanoes, which is why Yellowstone is such a subject. Tambora is on an island in the ocean. So it has limited, physical effect reach. The ash is the worst thing from Tambora. Yellowstone has a whole different kettle of fish. We'll talk about Yellowstone later on today. So there are a couple of different types of eruptions we're going to talk about today. First one being your more kind of explosive volcanic eruptions, like this. And the second being your more kind of, I call them calm-ish, where it's just like spitting, spouting lava and debris out. It's not really a kaboom. It's more of a bleh, 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 bleh. Right? What do you suppose controls whether or not your eruption is explosive or kind of just this calmish style?
The pressure build.
Pressure is definitely a factor, but what causes pressure to build more? Heat is a different factor. Heat, yes, definitely is a thing that's there. So focusing on pressure, what would cause, do you remember when we learned last time about the viscosity? What does viscosity do?
Oh, it's resistance to flow.
Yes, it does. It is. It is a resistance to flow. What is the biggest controlling factors on viscosity? It's going to be these things that we talked about, right? Your silica content. Huh? Yeah, I remember the silicon tetrahedrons we talked about, okay? The more of them there are that form, the more bound up your material gets. Then obviously there's the heat. The hotter it is, the runnier it is, just like with most things. Then there's the volatiles. What do I mean by that? Well, when you look at these 2 fluids here, tell me what they have in common. They're both, yes, they're both liquid. They both have bubbles, the gases. Yeah, so the bubbles, is that what you're pointing at? Yeah, so they both have bubbles, but what's the difference between the bubbles in the top fluid versus the one in the bottom? Is it disappearing? Releases where? Yeah, it goes to the surface. The fluid in the bottom there, which is water, is non-viscous enough that the gas bubbles that formed in it are able to rise up and escape to the lower pressure zones. The fluid in the top is so viscous that the gas bubbles that form cannot escape. So if I have a liquid forming bubbles, and those bubbles cannot escape, more and more of them keep forming and forming and forming, what's going to happen? What happens to my pressure specifically?
Pressure rises.
Pressure builds.
And it.
Right, so now I'll come back to my question. What do you suppose could cause an eruption to be more explosive or calm? The viscosity of my magma. Boom. Okay. So, just to recap what we talked about last time. We have mantle rock that for one reason or another rises up to the surface. Remember how we can get convection causes mantle to rise up, and then one of three things can happen with that geothermal gradient that can cause it to melt: decrease pressure, increase temperature, add water, right, to lower the melting point. You get your plumes of magma, which rise up here, okay, and then they come up through the crust, they pool just under the crust, and that's what can feed a volcano. Now, as that pressure is building inside of my volcano, as that gas is building inside of the magma chamber, eventually something's going to happen. The pressure builds up enough that whatever is above that magma chamber is no longer sufficient enough to hold it back. So just like when you open a soda, what's the first thing that comes out?
Carbonation.
Gas, yeah. And then the fluid, okay? Very foamy, filled with all sorts of gases. But you get that puff of gas, and then you get that kind of gas-filled foamy liquid, okay? That's exactly what happens inside of a volcano as it is erupting, okay? So, that's where we get these two types of eruptions. Calm-ish style eruptions have non-viscous lava. Man, excuse me. Non-viscous lava. I'm just gonna pop one of these in here. The cough is the worst. It always stays the longest. Okay. And so what happens to make my calmish style eruptions where I have non-viscous lava is eventually the magma chamber just fills up so much that it oozes out the top. It doesn't really erupt. It just kind of gets pushed out the top. Okay? With an explosive eruption, you get so much pressure building up from those bubbles that eventually the cork is forced out, right? Usually the top of the volcano pops off, and then everything is allowed to escape, just like with your bottle of soda there. This is drone footage from Mount Fagradalsfjall in Iceland, taken a few years ago. The guy that took this, his name is Bjorn Steinbeck, fantastic Icelandic artist, photographer. They flew hundreds of drones over this eruption. This is one of the only pieces of footage that made it out because most of the rest of the drones caught a piece of lava and fell in because they got melted. Isn't that incredible footage, though?
Looks like fun.
It does look like fun, doesn't it? I kind of want to show you that again. Hold on. Here we go.
You want to show us or you want to watch it again?
Yeah, exactly.
Yeah, I mean, why can't it be both? Okay, so look how quickly this lava is running. What's the composition, do you think, of this lava? Does it look viscous or non-viscous? So what would the composition be? If viscosity is tied to silica content, primarily, we're looking at something non-viscous, so low silica content. About what composition would that be? Hmm?
Looking at the wrong note.
Ah.
I was like, where are these in pencil?
What do we think? low silica content, low silica content, low viscosity composition. Cole, what do you think? Do you remember what our compositions are? The different igneous compositions? Why mafic?
Mafic has no silica.
Well, it definitely has silica. It has less silica, right? You remember there's that inverse relationship between silica content and iron magnesium content?
It has magnesium and iron.
Yep. Could you let her in? All right. Hello.
Hello.
Good morning. Yeah, no worries. Okay. So, mafic. It was mafic. And, I mean, did you see the rock around it?
It was like falling into it.
It was falling into it, sure, but what was the color?
Dark.
Very dark colored, right? Pretty good indicator we're looking at very iron and magnesium rich rocks there. So Iceland is made almost entirely out of basalt, okay, because of the composition of the magma that comes up through its volcanoes. All right. About 90% of all material that's extruded here at the surface is going to be mafic. 9% intermediate, 1% felsic. Why do you suppose that is? Why would so much more of it be mafic as opposed to the other two? Where do we tend to get mafic material the most?
That's more on land, right?
If it's not more on land, it must be more where?
In the water.
In the ocean. Ocean crust is very thin, remember? Ocean crust is very thin. Bowen's reaction series and assimilation, those two things that we learned about, they don't have as much time to happen. So we get mostly mafic material under the ocean crust. And then it gets pushed out onto the ocean crust. And how much of our surface is covered in ocean? Yeah, most of it. So logically, doesn't it make sense that most of the material that gets pushed out, most of the lava, is also mafic? That logic follows, right? Good. 9% is intermediate, 1% is felsic. Why is there such a smaller proportion of felsic material at the surface? It has more silica, which means it's more what? Viscous, yes. And if it has more viscosity, it can't what? It can't move. Yes, it can't flow as well. Good. So our felsic lavas, when they get pushed up, they don't make it very far, right? And that's why we have so much less of it here at the surface. Are you following all that there? Great. Okay. So mafic lavas can flow, they've been clocked at up to 30 kilometers an hour. It's pretty dang quick. You better at least be on a bike because you ain't outrunning that. Okay? Not unless you're Usain Bolt, right? And then felsic lava, you can barely even, most of the time you barely even notice it's moving, right? The few times that you would ever see it. So that's where that speed difference would come in. All right. You guys want to learn some Hawaiian words? Yay. All right. We're going to learn some Hawaiian words, and I'm going to pass around some rocks. All right. So these are different types of Same rock. All good? Okay. This is an igneous rock. Yes, from Hawaii. This is called A'a. Yeah, say it with me, A'a. Yeah. You know why it's called A'a? If you were a barefoot Hawaiian and you were walking on this, what would you be saying? Right? That's not why it's called that. I just like that joke. So this is, if you had to guess, you have a snake. I'll pass it right here. If you had to guess, what would the composition of that be, generally speaking? Why? Do you agree, you guys? Yeah, it's dark in color. Is there something that we can say about that texture too? Make some textural observations about that. What'd you observe about the texture in that, Cole?
It has like the little grooves and holes in it.
Yeah, what do we call those holes?
I don't know the name.
Starts with a V. Anyone want to help him out? Vaholes. No. Vesicles. Vesicles. That is a vesicular texture. Yeah. Okay, so A'a is what you get when you have a very low temperature. In what? Oh, in A'a? No. Like aha? No. It's a low temperature basaltic lava flow. That is basalt. That is a form of basalt. That is one of the ways we can find it. You don't want to get it?
I can see it. I mean, it's not one of these smaller ones.
No, it's not. Okay, so if you take the same material that makes that A'a, but it's a hotter temperature, meaning that it is flowing easier, you get a different type of rock forming. Pahoehoe. This is Pahoehoe. Yes, you can say it, Pahoehoe. Thank you, good job. All right, so when you get this and it cools off, it makes a sort of smooth, ropey texture, okay? Like ripples of water that got frozen in place almost, okay?
It looks like burnt tree trunk.
Kind of does, sure, yeah. It's got that kind of roundish sort of shape like a tree trunk. It is still somewhat vesicular, not nearly to the same degree as that one. Definitely the holes are a lot smaller though, right? So this is what you would get if you have that basaltic lava flow, but it's a higher temperature. So here we have our lava flow here at the surface, and you can see on the top where it's cooling off rapidly, you are making these pahoehoe deposits, not deposits, these pahoehoe kind of layers, okay? Surface layer there. But it's still flowing from underneath that top layer. Now eventually, as time goes on, it gets further away from its heat source, it starts to cool off. Oh, thank you. Hello, there we go.
Hello.
And it starts to cool off. It's going to take on a more A'a sort of appearance where it's just going to be rough, chunky blocks. Okay? Okay. Other fun volcanic things we can see. Lava tubes. Any of you guys ever been to Hawaii?
We don't have plasma.
Oh my goodness, you could. If you're older than 18, you can. Let's see. I used to live in Hawaii back when I was with my parents because my dad was stationed at Pearl Harbor. Excuse me. And if you ever go, there are some tours that you can have on the Big Island where they take you through lava tubes, which are basically just tunnels through the volcano, through the old volcanoes. The ways that the reason why these form is, imagine you have a high temperature flow, okay, like what we just talked about made the A'a, right? High temperature flow, very runny, and it's cooled off on the top surface. So you have this hard layer here, and it's kind of imagine if it had formed inside of a stream valley or something, like a little, some sort of low area. So we have a river of lava running through an area, and it's hardened on the top, so you basically get this tube through which liquid lava is running, okay? Like a straw. And then the temperatures slowly start to cool off. It goes from more pohoi forming lava to more aa forming lava because of low temperature. And so the top and sides of my tube have pohoi, so they make this sort of tube shape, and then the inside gets filled with aa, the rough, chunky blocks that are disconnected from each other, okay? The next time my volcano gets ready to erupt, that burst of gas is going to come out, right? It's going to go, and where's that gas going to go? It's going to follow the same paths that the last eruption did. And so that burst of gas is basically going to shotgun blast all the aa out the other end of the tunnel, leaving an empty tunnel. Now, assuming that there isn't actually any running lava as a result of this next eruption, that tunnel stays empty, and that's where you get these lava tubes that you can walk through in Hawaii. They're pretty cool. Then you have block lavas. These are just kind of fields of intermediate or felsic lava rock. And you kind of walk around and you're like, what are these doing here? What even is this? These are pretty rare because these are actually intermediate or felsic lava flows. They don't make it very far, which is why they're much rarer. But what happens here is your lava flows and starts to cool off. As it starts to cool off, it makes these blocks, these chunks. To imagine this, you ever seen mud dry out? What does it do? What does mud do when it dries out? It hardens, yes, but what else does it do? It cracks. Why does it crack? You want to take a shot?
Well, like it loses moisture, like that keeps it together. So
Yeah, it's definitely losing moisture that keeps it together. Its molecular structure is changing because you're removing something, the water. You're going from essentially a liquid, you could call mud a liquid or a semi-solid if you want, to a straight up solid, right? And so you are losing something. And because you are losing something, it's going to take up less volume. And as it takes up less volume, the chunks of mud retract from each other. They detach from each other and you get mud cracks. Same sort of thing going on here. Going from a liquid state to a solid state, it contracts in on itself to make that solid crystalline structure. And so you get from having this one uniform liquid flow to a whole bunch of broken, jagged, chunky blocks when it becomes a solid. Okay, so that's how those are. That's what happens there. Then we have pillow lavas. Pillow lavas are pretty cool. This is what happens when lava is flowing underwater. Okay, so the lava is continually pushing forward, but it's also continually, instantly getting quenched on its top surfaces that are interacting with this water. So it's always pushing forward, shoving aside the hardened stuff ahead of and on top of it, making what we call pillow lava. Isn't that cool? Yep. This is what lava flows in the ocean look like. Okay. Now let's talk a little bit about those gases that build up in these magma chambers, okay? Depending on the composition of my lava and its heat and a few other things, it can have anywhere between 1 to 6% volatiles in there. Okay, what is that? What is a volatile? A volatile is some component that when you change characteristics like heat or pressure, change part of the environment, it could turn into a gaseous state and increase the pressure inside of that magma chamber, which could cause an eruption, okay? Most of the time, it's water. So about 70% of all gases that are removed from or that come out of a volcano are water. Then there's CO2, nitrogen, sulfur dioxide, all that stuff. And a single eruption can release thousands and thousands of tons of this stuff on a daily basis. Out of curiosity, those gases, nitrogen, CO2, water vapor, Where else do we find those?
Nitrogen and silver and oxygen. I don't think that's it.
Okay. Where else do we find these things? These things, water vapor, CO2, nitrogen, even sulfur dioxide, where else do we find these gases?
The atmosphere?
Yes, the atmosphere. This is actually where our atmosphere came from, my friends. Billions and billions of years of volcanic eruptions have built up the concentrations of gases in the atmosphere. Our atmosphere early on used to have a lot more carbon dioxide, a lot more sulfur dioxide, and other gases like methane. But as time went on, and eventually you form life develops. We'll talk about this more in 1404, those of you that take it from me. You get chemosynthetic organisms that absorb the sulfur dioxides, crack them apart, and then release oxygen, right? So our atmosphere right now is mostly nitrogen with oxygen and other things like argon, carbon dioxide, things like that, okay? You and I mostly rely on the oxygen, but our atmosphere is actually mostly nitrogen. But yeah, it was made through all of these volcanoes. Okay. When a volcano erupts, there's going to be a whole lot of side effects, I guess you could say. One of those is going to be the creation of these pyroclastic materials, okay? So remember we were talking about pyroclastic texture as being the only kind that doesn't directly come from lavas or magmas? It's from the results of a volcanic eruption, from the fragments that are created as well as the ash that is released from that. So pyro means fire. I think everyone is probably familiar with that. Clastic means fragment, okay? So the result of these eruptions. So there are a couple of different classifications we have for the pieces from these things. Ash is anything smaller than 2 millimeters. I just passed around a container of Mount St. Helens ash. Did that end up with you? Ulani, did you get to see the ash over here? So that is some ash from a volcano called Mount St. Helens that erupted in 1980. Yeah. And then there's lapilli, also known as cinders. They are anything up until about that big, give or take. Okay. And then you've got bombs. Bombs are what you get when you have a sort of semi-solid material flying through the atmosphere. Everything okay? Oh yeah, here, don't pull on him.
He's so mean to me.
He'll find his way out. Just actually, he may have gone down into the pedestal.
No! Look, I see his head.
You see his head? Where is it?
Here. Whoa.
All right.
Josh, don't hate me.
Don't what?
Don't hate me.
Why would I hate you?
Because your son is rebellious.
Yeah, no, he went down in there.
No, Josh. Josh, don't kill me, please.
I'm not gonna. Hold on.
Am I in trouble?
No.
You promise?
Yep.
Okay.
Come here,
Has
buddy.
he done this before?
Nope.
What?
All right, I'm gonna pick this up
Okay.
and we're gonna pull him out.
Okay.
There we go.
You're not allowed under the door.
Yep, good idea. All right.
You're bad. You're trying to get me in trouble with Josh.
Lava bombs. All right, so this is a lava bomb. So when you get rock that is partially melted through a volcanic eruption, you okay?
Now my neck hurts because your rebellious son.
Please. We're hardly even related. You get a semi-melted material flying through the atmosphere. It's going to take on a kind of an aerodynamic shape as it flies through the atmosphere. Same reason why a raindrop takes on that kind of raindrop shape as it falls through the atmosphere. things naturally take on aerodynamic shapes if they're moldable, liquid. So the semi-melted rock is going to take on this interesting kind of streamlined shape. And then when it lands, it's usually already become solid, so it makes kind of an impact, which is why we call them lava bombs. It tends to be pretty destructive when it lands. That's also a lava bomb there. All right. Thank you. I forgot to put those away because some things happened after class on Tuesday, like I mentioned. Okay, so do you remember when I played that video earlier of popping the cork off that soda?
I don't think that was a soda, but yes.
I'm going to pretend it was soda because this is a college classroom.
That didn't look like a soda.
It probably wasn't, but we're going to act like it was.
It was totally a soda.
It's totally a soda. It was root beer. You didn't see that was root beer? I saw it was
Yeah,
root
in a
beer.
green bottle with the gold wrapper around the
Yes.
top,
Yeah.
sure.
All right, fine. It was Martinelli's. All right. So when you pop the cork on that Martinelli's, what was the first thing that came out?
The carbonation, the gas.
The gases. What was the next thing that came out?
The liquid.
Liquid, but it was super aerated, right? It was just filled with all those gases. Very foamy. So the foam that you get that comes out of a felsic style eruption, where you have a lot of silica, it tends to come out and then get so it's filled with gases, but then it cools off very quickly. That's what makes your pumice, we talked about last time. Okay, this is the rock that floats on water and they use in spas.
Oh, the pumice.
Yeah, the pumice. So it's the foam that comes from a felsic kind of eruption. This is scoria. It's the same thing, but you'll get this from a more mafic eruption. You can definitely tell there's a lot more iron and magnesium in here than there is in this one, right? Okay, now the iron and magnesium in here makes it too dense to float on water, but you can tell it's still filled with holes just like this one is. There you go. It's okay.
So embarrassing.
Yeah, it's okay though. You'll be fine. He'll be fine. No one got hurt. So,
Cord under the table, he was wrapping himself around.
you know the pedestals under the tables? Some of them are hollow for power cables to come up so you can plug your stuff into the tables. Yep. So he went under the table and then started going down the pedestal, the hollow pedestal down there. So I just picked up the table and we pulled him out. It's all right. It's no big deal. Devil, yes, troublemaker, which is, I mean, it's not though, because he's the sweetest snake you'll ever meet in your life.
He's sweet to me until he goes under the table and then gets stuck and then makes me look bad.
No, just think of him as curious. How about that?
Curiously, in a bad way.
Okay.
Not the Taz.
Thank you, Chloe. Okay. So this is our general volcano design here, okay? So volcanoes generally have this sort of cone shape, inside of which is a conduit which goes down to the magma chamber. When the conduit reaches the surface at the top of your volcano, it's called a vent, and the vent is inside of a depression that's made from the last type of the last series of eruptions we called a crater, okay? Every now and then, you'll see lava chew its way through the side of the volcano and start spilling out the side. We call those parasitic cones. I have another sneeze coming. Whenever the magma underground starts rising up to the surface, getting closer to the volcano, and it's gearing up for an eruption, it's going to increase the temperature of the ground around the volcano. And when it does, it's going to make the ground water, so all the water that's in the pore spaces of the rock there, all that groundwater is going to heat up, and you'll get these things called fumaroles around the outside of your volcano, around the perimeter of your volcano. So the fumaroles are basically steam vents, and you can measure the gas and acid concentration from these fumaroles, get some information from there about the likelihood of when this volcano might erupt, okay? So if the gas concentration in that water is increasing, it might be a good indicator. Or if the number of fumaroles are increasing, there might be more heat, right? So this is that same volcano, Fagradalsfjall. It's not that far from the capital of Iceland, Reykjavik. So these are all people out on their lunch break who just went to go watch the volcano erupt for a little bit. Actually, I think Iceland has a lot going for it as far as surviving most things that could happen to us. They're already very isolated. There's only one way in or out of the island. So if there was like a global pandemic, like this is what happened during COVID, they just shut down and like they were fine.
But if they had to like evacuate, like because it wasn't something that they could isolate from, like it was in their area, I think they're.
Well, then they're also very easy for us to isolate. Is that what you're talking about? Like something starts there?
Population like that.
Hey, you were the one that just said natural selection.
Talking about like 60 people.
No, Iceland is gorgeous and very self-sustaining. Like they have everything they need for the basics of life. They could keep on living despite whatever is happening in the rest of the world for the most part. Okay. All right, so there are 3 different types of volcanoes. Shield volcanoes, cinder cones, and composite cones. Shield volcanoes are by far the largest type of volcano. Very low, definitely still that kind of cone shape, but very low angle cone. And then you've got your composite cones, like this is your Mount St. Helens style cone, okay? And then cinder cones, which are the smallest type. So let's start off by talking about shield volcanoes. Shield volcanoes are generally underwater volcanoes, which means that they are what kind of composition? Huh? What composition of lava generally occurs underwater? Yeah, mafic. Which means that we're going to get very non-viscous lava, which means that the lava can come up and flow out very easily. So because the lava is coming up and flowing out and coming up and flowing out, it goes pretty far before it solidifies, right? Which means that we get very widespread, thin layers of basalt. And these widespread thin layers of basalt pile up on each other like a stack of pancakes until eventually my volcano breaches the surface of the ocean at the very top. That's how you get islands like Hawaii and Iceland. Okay, that's how those formed. The Hawaiian Islands are actually much larger than what you see at the surface expression because they spread out pretty far on either side all the way down to the bottom of the ocean. Okay. Cinder cones are very, I say they're very small. Compared to the other 2 types, they're the smallest type. They also tend to be the most short-lived. They can pop up out of nowhere very suddenly, but then they'll all of a sudden just die. Cinder cones are typically what happens when some offshoot, some vent branches off from a magma chamber and pops up at the surface and provides just enough heat to spit out an eruption for maybe a year or 2, and then that's it. So not a full-on volcanic eruption per se. These are definitely types of volcanoes, just not what you think of when you typically think volcano, okay? There's also not usually lava associated with this. This one that I have here, this picture, this one has some lava with it. That's atypical. That is not normal for a cinder cone. Normally it'll just spit out some scoria, a whole bunch of cinder and lapilli. That's what builds up the sides of the volcano there. So just as an example, there is a story of a cinder cone from Paracutin, Mexico, where this guy, this farmer, was out in his woke up one morning and went out to his fields, and as he was leaving his house, one of the nearby fields, he saw that there was like some steam coming out of the ground. He was like, "Oh, well, that's weird." But he didn't really think anything of it. He wasn't a scientist or anything. He was like, "Oh, I'll deal with that later." So he went out and worked in the far fields for the day. Over the course of the day, blue sky, not a cloud to be seen. He hears what sounds like thunder. Doesn't make any sense. Can't figure it out. End of the day, he comes back to his farmhouse, and where the steam was coming out of the ground, there is now this gigantic crack, and there's like fire coming out of it, is how he described it. And so he panics, can't find his family anywhere. The house is abandoned. So he goes into town, finds his family there. They had run there once the fire started doing its thing. And by the end of that year, that vent on his homestead had become a 330-meter tall cinder cone. And this one did actually spit out some lava, and it covered the town in lava. There are pictures you can look at online of the town chapel. Their church has dried lava halfway up the church. They had to abandon that area. And this thing stayed active for about 9 years. Died in 1952. That was it. Not a burp since. So they can pop up out of nowhere and then they're just done. Some live longer, some live shorter. Most live shorter, actually. And they're no, it just comes up out of nowhere, like flat ground, and then over a year. No, cinder cones aren't really the result of tectonic plates colliding. Cinder cones tend to be the result of a local kind of like heat escape. So if I have a magma chamber over here, and it might be feeding some bigger volcanoes over here, or maybe it's just sitting under the surface, cooling off. Occasionally, some of that magma is going to kind of wiggle its way out and pop up over here. Not really enough pressure or heat to cause a full-on volcano, but just enough that it spits out some stuff and heat and gases and stuff, and it makes a cinder cone. That's basically what this is. We actually have quite a few in our neck of the woods. There's a bunch in Arizona, a bunch in New Mexico, a bunch here in West Texas. They're old.
It cracks like through the ground and then slowly spits out lava before we come out.
It doesn't. So this kind doesn't usually have lava. I know the examples I gave do, but most of them don't actually have lava. So like the scoria that I passed around and that lava bomb that I passed around, that sort of material gets spat out and then makes the sides of my volcano here, just as time goes on and it piles up on itself, spitting out and piling on the side.
That's what I was confused about. How are we just like having these bubbles form on land?
You mean like
Not like bubbles, but like the mountains that come on flat land.
yeah, so material that comes down from underneath that's getting pushed up to the surface, but not really hot enough to make an explosion per se. Now we want to talk about explosive volcanoes. That's when we talk about composite cones. Composite cones are also called stratovolcanoes. These are the most dangerous kind of volcano, okay? This is your Mount St. Helens type eruption. These are the most explosive because there is the highest viscosity lava associated with them, which means that a lot of gases can build up, a lot of pressure can build up before the kaboom happens. Most of them are in the Pacific Ring of Fire, which I showed you a map of before, and I have another map coming up here in a minute to talk about it. But all around the Pacific Ocean, that's where most of them are. And there are a lot of different ways that these things can kill you. Yeah, so we're going to talk about them.
Like putting a camp near one.
Putting a camp near one, right. So the first way is through what's called a pyroclastic flow, also called pyroclastic clouds. So that first, when we pop the cork on that Martinelli's, right, and the first puff of gas came out, now imagine that Martinelli's bottle is now a volcano, and that puff of gas is now 400 degrees Celsius. So you pop the cork, puff of gas comes out. Hot gases do what? Expand. So you get this massive cloud of gas that's spreading outward, gas and ash, that's spreading outward, and it's going to incinerate everything in its path, okay? Extremely quickly. These things can move up to 200 kilometers an hour, okay?
So it's hot air melting.
Hot gases, yeah. This is a video of a pyroclastic flow from Japan. The guy did end up getting in the car, by the way. Just not initially. Oh, can someone let Cole back in? Thank you. Have you ever heard of the town of Pompeii or the... Yeah, Pompeii. Pompeii was a town in Italy next to Mount Vesuvius. Okay. And in the middle of the night, Mount Vesuvius erupted, and the pyroclastic cloud washed through, blasted through Pompeii, and also the other city, Herculaneum, but no one ever talks about Herculaneum. Went through both towns and killed everyone as they slept. Okay? So quickly that, like, no one even had time to get up, really. And you're like, well, how do we know that? Well, I'll tell you why we know that. Because it instantly incinerated everyone's body so quickly and deposited layers of ash over them that as the ash was forming on top of everyone's body, their bodies incinerated, leaving behind voids in the cooling ash in the shape that their bodies had. So in the 50s, when people were doing exploration of Pompeii, they found empty spaces in the ash in the shape of the bodies. You fill those empty spaces with plaster and then chip off the rock from around it, and all of a sudden you have plaster casts of everybody in the shapes that they were in. See, this guy's just getting up. Like, oh, what was that? And then that was it.
Oh.
Mothers of children, small child there. This is a dog. That's how quickly it happened. So that's a pyroclastic flow. Okay. Next thing that can kill ya. Lahars. Should I say that with a little less enthusiasm? Let's talk about the next thing that can kill you. Okay, lahars. A lahar is what happens when the temperature heats up, the temperature of my volcano heats up before it erupts, and that does something to the surface. When you're looking at a volcano, what does it usually have on its surface?
Snow.
Yes, thank you. Snow. Snow and ice.
Oh, yeah.
What happens when you heat up the surface of your volcano?
It melts
It does. And where's all that water going to go?
down.
Downhill. Well, it's not getting steamed. It's just melting the ice and snow, right? So all that melted ice and snow is going to go downhill, and it's going to go downhill fast. It's the sheer quantity of the water flowing downhill off this volcano is going to...
It's like a
Oh.
odd land tsunami.
Tons of gallons. No, we're talking about hundreds of millions of gallons.
Cute.
Yes. What?
It's like an on land tsunami.
It's essentially that, okay? So it washes away everything in its path. Towns, bridges, people, houses, picks it all up, carries it downhill. So that's a lahar, okay? So for reference, this is a person right there. And that mud line on this tree, that's as high as the lahar got.
Oh my god.
And it ripped up all of those trees and carried it with it
Where does it stop?
whenever it hits the ocean. Or an area flat enough for it to lose its energy.
If it were on an island, it would just clear out
To the ocean you go.
Very possible. Yeah, well, I mean, very possible depending on where you are. So when this happened, there was a town called Nevado de Ruiz in Colombia where a volcano erupted in 1985. Okay, in the Andes Mountains. Okay. Or I don't remember if it was in the Andes or if it was in the other one. I don't remember where it erupted, but it was high up in the mountain range, and the volcano eruption itself wasn't a threat. They weren't worried about it, so they didn't do anything until a lahar swept through and killed 25,000 people. Natural selection. Or governments that don't pay attention. Yes, right? So obviously, very, very dangerous. In our own nation, this is a threat. So can anyone tell me where that city is? What city is that? How do you know?
Grey's Anatomy.
Grey's Anatomy.
No,
The Space Needle.
but also Grey's Anatomy.
Which is also really funny to me that everyone identifies Seattle with the Space Needle, but almost every major city in Canada has a Space Needle. It's really funny to me. Yeah, that is Seattle. And that is Mount Rainier. Pretty dang close. So I used to live at a town called Ording, right here at the base of Mount Rainier. In Ording, on the first Monday of every month, we would have lahar drills. So all the sirens in town would go off. It sounds like an air raid siren. And everyone in town is supposed to pack up their stuff and practice leaving so that we can get out of Dodge before the lahar takes out the town. Let me tell you a little bit about Ording. There are 3 ways out of town. There's a road that goes up the volcano. It's not ideal, right? There's a road that follows the valley, which the river that comes off the volcano and goes through town is right there in that valley with you. The whole reason why you have to evacuate is because that river exists and the lahar would come down the river, right? So you don't want to go that way. The only real way to get out of here is to go across a bridge over the river and then up the side of the valley. That's the only viable way to get out of town, okay?
I want canes. I want canes too, now that she said that.
Oh, man.
Bro, you're a genius. I want canes now.
Well, I got called into work, so he's gonna go get us food. Before we both have to go to work.
Damn, I know what I'm eating.
I'll make a comment on that after I finish this thought. So the only way to get out of this town is to go over the bridge and then up the side of the valley. They only have about 8 minutes between when the lahar sensors would pick up the lahar and when the lahar would take out the bridge. And there are 7,000 people in that town. How many people do you think practice getting out of town on the first Monday of every month?
All of them? 0.
7,000 people know that they're not getting out of town in 8 minutes.
That's actually a good point.
So no one bothers to try.
Might as well just die.
See, that one's not even natural selection, that's just.
That's
common sense.
poor planning on
but
whoever
see,
built,
though, since
but they
nobody's
didn't
gonna
know,
do it,
right?
Natural selection will keep
When the
you
town was established, in the late 1800s, nobody knew this. Nobody knew it. Now we do.
weren't as geology.
Well, and volcanology wasn't as much a thing, and all of this. So
But see, that's a genius play, because then if nobody's gonna go, you have a path to get out.
I'm sure a few enterprising people will do their best. But let's say my kids are in school. Do you think I'm going to be able to pick up my kids and leave in 8 minutes?
No,
Exactly.
Don't have kids.
Oh,
Underground one?
it's just so you can dig your way out of 20 feet of mud?
Who knows? I didn't say it was a short-term thing.
All right. Now, on the subject of raising canes, this is probably an unpopular opinion, but I find it incredibly mid.
I hate you.
I know.
You're so ugly. I hate you.
Yeah, raising canes is tasteless unless you have some sauce with it.
Well,
I think they would make so much money if they would make spicy tenders.
See, if you made it spicy, then I'd probably enjoy it more, but it's just bland chicken.
well, I can't say that because I eat every meat that goes in my mouth touches ketchup first. So I don't know.
This is true.
I just eat every single meat with ketchup.
This is true. Yes. No.
Yes.
How un-Texan of you.
I'm
What
sorry.
was it that we ate that you like brought your own ketchup packs for that one time?
Was it when we had? Was it DQ when we had it?
Maybe. maybe.
could be.
But she didn't trust that whoever brought us dinner. This is when we were practicing one of our last rehearsals at the theater before we did our play a couple years back. But she brought like a dozen ketchup packs because she didn't trust that people would bring enough for her to have. And I don't even remember what the meal was, but I don't think it was something you typically eat with ketchup. She's crazy. Can you believe that I can say it was a couple of years ago now?
Ew.
I know.
Oh, that's so funny.
All right, calderas. Oh, actually, before I move on to calderas, I want to mention one more way volcanoes can kill you. You remember that ash that I passed around?
Yeah, ash
Yeah,
itself.
ash. Do you know what ash is? I think I mentioned this on Tuesday.
It's small flakes of fire.
Flakes of fire? No. It's glass. Microscopic shards of glass. Now imagine that you are in an ash fall because you're near enough the volcano for that to be a problem. You're breathing that stuff in. What do you suppose microscopic shards of glass do to your lungs?
Oh, it's like
This might be the worst way. This might be the worst way that volcanoes can kill you. If you're close enough to the volcano that the ash is just like, it's in the air and you're not like filtering it, your lungs get sliced up and you drown in your own body fluids.
That's so gross.
Yeah. So there's just another fun way for volcanoes to kill you. That would be fun. Like Mount Rainier erupts and they have to deal with it. That could be a whole season worth of content. Aren't they on like season 26? 23?
I don't know.
All right. Mount Rainier needs to erupt and that needs to be the final season.
I started watching it whenever they got, I think, like season 21, and I haven't caught up yet because I was so busy with school, I wasn't able to really pay attention and stuff.
Yeah.
So I restarted it again when I moved.
My wife has watched that show at least a dozen times. She rewatches Parks and Rec, The Office, Grey's Anatomy, and I think that might be it. New Girl. No, she watches New Girl. She watches those 4 shows over and over again.
Three reasons why I watched that show: Patrick Dempsey, Eric Dane, Jesse Williams.
Crushes. Got it. Cool. I rarely watch the same show over again or movie. Like, even if it's my favorite thing, I watch them, it's like, oh, that was really good. And then I just remember it. So unless I want to show it to somebody, I almost never watch them again.
I'm gonna start binging Shameless again.
The one show I consistently watch over and over again is Golden Girls because I grew up with that.
My little
Nice.
brother cried when Betty White died.
Yeah, that was big loss. That was a big loss. Betty White was such a classic.
She was.
But he was like 8 at the time.
Did you ever see Betty White and Ryan Reynolds interacting with each other?
No.
Oh, it's so funny every time.
Oh.
Those two would just rip at each other. It was hilarious. You should look up some videos of it sometime. Okay. Calderas. Calderas are what happen when a volcano erupts so powerfully that one of two things happens. Either it completely self-immolates, it's completely destroyed in the eruption, which has happened, or the eruption is so intense it empties a significant portion of the magma chamber under the volcano, and the weight of the volcano collapses down into the magma chamber. So Yellowstone happened when the last eruption was so powerful. Again, remember, a supervolcano. It was so powerful that magma chamber underneath it was partially emptied, and a huge chunk of the crust fell down into it. The Yellowstone caldera is 15 kilometers across. That's how big that volcano is. If you go to Yellowstone National Park, the entire park is the volcano.
Okay,
What?
what is that in like miles?
15 kilometers?
Yeah.
Yeah, we need American
We need
numbers.
conversion.
Okay, all right. Like, is that 11? 12? I don't know.
You're saying this in like the questioning tone, like we know the answer.
I work in scientific measurements.
Not again, Laura. You're not American.
Sorry, will someone Google it? What is 15 kilometers? Because I think science. I don't think American.
I know you love the name. I know you do, but I'm really embarrassed to get this answer for you, okay?
9.321 miles.
9.321 miles. Okay, well, that's how big the caldera is. Okay. Now, Crater Lake, which I have a picture of up there, it's kind of falling off. I have to get a ladder and go up there and fix that at some point. Crater Lake.
Bristol Lake. Now I know the crater.
Yeah. So this is a picture of a different caldera, but I'll come over here and show it to you. Woo! Okay, so this is Crater Lake, in Oregon.
Is it actual crater?
Yes.
How's there a mountain in it?
That's called Wizard Island. That is something that I will bring up in just a minute here. Okay. But Crater Lake formed when the eruption was so powerful that it absolutely just destroyed the volcano, literally leaving a crater that filled with water.
So it like explodes and then falls back in.
The eruption was so powerful that the entire volcano went kaboom instead of just out the top, or like Mount St. Helens out the side.
Did that kill anybody?
Well, that happened, I want to say 600,000 years ago or something like that. I don't remember exactly when Crater Lake erupted last.
Might have killed some Native Americans.
Not at that point, no.
Oh, okay.
No. There are no Native Americans around there at that point. As far as we know, this is again another thing we talked about in 1404. The first humans to emigrate across to North America was about 13,000 years ago.
Oh, okay.
Okay. So when you have magma making its way to the surface, but it's not in kind of this conduit tube, oftentimes it will follow natural cracks like fault surfaces. Like we have, not really like trenches. A fault is a crack in the ground, which is where earthquakes happen, but they are a natural zone of weakness in the crust because it's already somewhere where it's broken. It's and so you'll get these flat surfaces along which magma can travel sometimes, and when it does, it doesn't come up in one spot that makes a volcano in that one spot. Instead, you'll get this long, we call them fissure eruption, where lava is getting pushed out along those crack systems. And these will often form what we call basalt plateaus, which are very, very, very wide expanses of basalt rock that just get piled on top of each other in that stack of pancakes sort of format I told you about before. This happens a lot in the ocean, but also we see these happening on land. A substantial chunk of Montana and Idaho are covered in basalt from these style of fissure eruptions. Well, it wasn't apart. It doesn't need to have been apart, but it does add more layers on top of it. All right, now lava domes. Now this is what Emma was asking about with that island there, that Wizard Island in Crater Lake. This is Mount St. Helens now. You see this little guy right there? This cute little baby volcano. Yeah, it's a cute little baby volcano growing out of what's left of the old volcano. That's exactly what it is, actually. So right now we call it a lava dome. It's essentially the new plug, okay, the new cork on the bottle. Every now and then, there's a minor eruption, which spits out a little bit of lava, ash, debris, and that builds up on the sides. And then another little eruption, and then another little eruption. And as time goes on, it builds up, builds up, builds up, builds up, until eventually there will be a big one. But every time there's another smaller one, it adds to the mass of the inside here. And so it's building up this tiny little volcano so that eventually it's going to get bigger, probably fill back in this empty space that was there. Okay, so Wizard Island was some of that, a little bit of continual eruption after the fact. No longer active. Crater Lake is completely dead, but that's how that happened. Okay. Volcanic pipes. So we've talked about how inside of your, excuse me, inside of your cone, okay, there is a conduit. That's how the lava or the magma comes up to the surface to become that lava, right? But what happens when my volcano dies and all the magma inside of that conduit crystallizes? As time goes on, my volcano is going to slowly weather away. It's going to fall apart. It's going to break down. But that conduit of crystallized magma is usually made out of materials which are harder than what the outside of the volcano was. So a volcanic pipe, like this one, this is called Shiprock in New Mexico, this is what's left. This is the conduit of a volcano that used to be on top of it, but got weathered and broken down. So where that pipe is, there used to be a much bigger volcano there, but it's not there anymore. The conduit took a lot longer to weather away than the rest of the volcano, and that's what's left. Sorry, it's so gross.
No, I was thinking about the conduit.
Mm.
It's just kind of weird.
It's a little weird.
They kind of look freaky.
Yeah, it kind of, when you see something like that, you're just like, that's not quite right.
Yeah.
And then you realize what it is. They call it shiprock because from a distance, people traveling in the desert thought, is that a ship? Because it kind of, from a distance, it kind of almost looks like a sail.
Oh.
And so people were like, no, that can't be, are we near the ocean? That can't be right. They thought they were like hallucinating, and then to get closer and realize it was a rock.
Why is there so many of them though?
So this is the actual conduit here. And then these are dikes that spread off of it. Remember, a dike is an off branch.
Oh.
Yep.
So the big rock one is the conduit.
This is the actual conduit. So this was the basically vertical tunnel through which the magma was traveling up to the volcano that used to be there. And then this is an off-branching dike from the conduit.
Well, that makes so much more sense. Because I was like, how does all that magma get through your tiny tubes?
Yeah, no. No, that was just a little side thing there. Okay, so this is that picture I promised you I was going to bring up. This is the Pacific Ring of Fire. What is that in Finding Nemo? Isn't that like, the Ring of Fire? Right?
Yeah.
I have to say it like that every time. All right, so this is our Ring of Fire. Most of our composite cones are going to be around this edge. You see all these black triangles? Those are composite cones. Most of them are there. Not all of them, though. There are a few up here in the Himalayas. Why are there some in the Himalayas? What's happening in the Himalayas?
The plate tectonics
Yeah, what plate tectonics specifically?
going together.
They are colliding, right? We call that a convergent plate boundary. So two plates are colliding together, converging. That's creating a lot of heat, a lot of pressure, boom, bada, boom. You get volcanoes. Okay, so that's why there's a few out there. All right, well, let's see. Why are there so many here in Europe?
Same thing.
Well, what's happening?
Those are the fabric. No?
Still converging. I don't think I've talked about this yet because we haven't talked much about plate tectonics specifically. Africa is currently colliding with Europe. Yeah. The Mediterranean Sea is eventually not going to be there anymore. It's going to get squished. There's going to be another mountain range there, like the Himalayas.
So, but it's also just trying to create food with big cracks.
Not in a second.
Pangea becoming one again.
No, we'll never have Pangea again. Pangea came and went. But what we will have is a new kind of megacontinent. You can't call it a supercontinent. A supercontinent has to have 75% or more of Earth's land mass. Okay? But when Africa and Eurasia collide together, it's going to be more like, what was it? 63, 64%? Kinda, yeah. Okay, so they're going to collide together. It's going to become this big old megacontinent. We're going to have a whole bunch of stuff. That's why all these volcanoes are here, is because Africa is colliding, making a whole bunch of convergent interactions, causing all of those.
So that's when they will literally move.
Yeah, Italy is going to get squished.
Oh,
Yeah.
not the boot.
The boot.
The boot gone.
Yeah. Okay, now something that Emma was just talking about, somewhere where it's splitting apart, that is right here. Saudi Arabia and Africa separated from each other. The Red Sea is right there. This is a divergent plate boundary. Okay, the Red Sea going into the Gulf of Oman right there. That's a divergent plate boundary. So Africa's kind of unzipping that way while colliding that way. But it's also unzipping right here. That's where this chain of volcanoes is coming in. There is an offshoot of this divergent plate boundary That's created a divergent plate boundary right here. So we are actually seeing Africa get unzipped right there. Okay? It's breaking apart. Yeah, give it another 20, 30 million years, there's going to be a Red Sea type offshoot of or ocean right there separating West Africa and East Africa. Okay? So these are all the different interactions we got going on right now. Okay? Now notice as well, volcanoes don't necessarily have to occur next to a plate boundary. Can you give me some examples where we have volcanoes without plate boundaries? The plate boundaries are where the tectonic plates are colliding or separating from each other. Yeah, Yellowstone's right here. Good. It's not on this map, but it's there. Can you think of another one that is on this map? What about... Didn't you make fun of me earlier because you were like, we don't have plasma money to go to Hawaii? Yeah, Hawaii, nowhere near a plate boundary. It's in the middle of the largest tectonic plate, the Pacific Plate. So why are there volcanoes? Why is there a volcano in Yellowstone? Why is there a volcano in the middle of this plate? Remember that question. We will come back to that in just a second. So we have our convergent volcanism that is happening as plates collide with each other, generating a lot of energy and creating a lot of pressure. Then we have our divergent volcanism, where two plates are separating from each other, creating space for mantle to rise up, lose pressure, and create magma. That's what's making those two different types of volcanic environment. Okay? Then we got intraplate volcanism, like what's happening with Hawaii and Yellowstone. So it's happening in the middle of the plate. It's not associated with any of that, with any of the plate activities. So what's happening here? Well, remember when I taught you about convection? I told you about lava lamps. Okay, so we have a heating element. Think of that as our core. Our mantle rock is sitting on top of it, heating up. As it heats up, it gains, as it heats up, it expands, gains volume while maintaining mass, decreasing density, and it rises up to just underneath the crust. Okay? There is no rule that says that can only happen near a plate boundary. It's just where that happens to occur near a plate boundary, according to the rules of the wow, the word just escaped my... I know, it's there. Gosh darn flu brain. Yeah. The rate at which heat increases the deeper you go underground.
Wait, what? The rate at which
Heat increases the deeper you go underground is the definition, and the actual word is there somewhere. Geothermal gradient. Oh my gosh.
What?
Geothermal gradient.
Oh, yeah, I never would have said that.
I'm sure you would have gotten there eventually. Okay, so this is rising. Well, what happens if it rises underneath of a plate? Well, it eats its way through the plate, chews its way up to the surface, and then you get volcanoes there as a result of this hot material just under the surface. Now, for Hawaii, it happened in the middle of the Pacific Plate. For Yellowstone, that happened in the middle of the North American Plate. Yellowstone, though, is a very cool, unique circumstance. Yellowstone has a very, very large, very hot magma chamber, which is actually very close to the surface. Most continental volcanoes, their magma chamber is 10 to 12 kilometers deep. Yellowstone's is only about 5 kilometers deep, which is why we watch it very closely, not only because of the size of the eruption that could happen with Yellowstone, but because also it's so close to the surface, the magma chamber is, that we would have way less warning before it happened. Yep, it has pooled underneath the surface at a certain depth. She said 8. I was just agreeing.
Raising Cane's, and now she's
Well, if you're gonna eat something, at least eat something good.
Raising Cane's is good.
Okay, what would you put above Raising Cane's?
Chick-fil-A, hands
Chick-fil-A
down.
is ass.
Wow.
Their breakfast is good, but everything else is ass.
Wow.
I
Wow.
would put Chick-fil-A above only for price. I think that's
Above what?
Chick-fil-A above Cane's only for price. It's cheaper.
Oh, for price. Raising Cane's is more expensive than Chick-fil-A?
What we get.
Well, I definitely don't want to go there again now.
We spend maybe like $25 at Chick-fil-A. You spend like 30 at Cane's.
Also Popeyes. I would put Popeyes above Raising
I
Cane's.
think Popeyes maybe 3 times the amount.
I've never eaten there, so.
I think the closest one is in Lubbock.
I thought we had one.
There's one in San Angelo.
There's one in the mall.
Yeah, there's one near the mall. It's like behind it.
I have never seen it.
No, you're right. Yeah.
Because I think it moved in there when that weed whatever place went out.
Is it new?
No, it's been
It
there for a
looks-
while, bro.
Run down.
Huh. I did not know that.
But even then, there's one in San Angelo.
I never go to San Angelo.
2 hours away.
So's Lubbock. Okay. So this is just a graphic that's kind of showing you the different interactions that can happen, which can cause the different types of volcanism we've talked about today. So rift valleys forming, like what's happening here in East Africa. This is a subduction of an ocean plate under a continental plate, interplate volcanism. This is just kind of a reference guide for you to remind yourself about all the different types and locations where they can happen.
Okay. Thank you, Jeff.
You're welcome. And then finally, the last thing I want to talk about is how do you live with these things? Well, living with volcanoes is something that we've had to do for a very long time. And we've learned how to adapt to them in certain ways. But absolutely, 100% they deserve our respect because they still kill people all the time.
Really?
Yes.
I haven't heard anything.
Oh my goodness.
That's like recent one.
Yeah.
The most recent major volcanic eruption was in East Russia. They had an 8.0 earthquake last year,
Oh.
which was so powerful. The earthquake was so powerful, it caused a nearby volcano to erupt.
Oh, so it like triggered it.
It triggered
Yeah,
it.
it was tsunami.
Yeah, there was a tsunami.
Oh my gosh, all the.
Yeah, it hit all of the things. Anyway, so yeah, so they erupt all the time. People still die from these things, especially in parts of the world where information about how they work and how you can survive them and how close not to be to them and all of that still hasn't been shared. But how do we monitor these things so that we can try and be better about keeping an eye on them? Well, earthquakes,
Gatekeeping information.
rare gatekeeping. Luckily, in what we consider first world countries like the U.S., we don't really gatekeep information about natural disasters so much. In other countries where they rely more on their populace not knowing as much, they still do that. But earthquakes are one way that we monitor them because all of that rising magma is going to cause some shaking to occur, right? Rising mass is going to cause displacement. That displacement causes shaking. So we can record that, and if we start seeing minor earthquake swarms around a volcano, that might be a good indicator it's getting ready to erupt. Expansion, like what happened with Mount St. Helens before it erupted. If it's filling with magma, it's going to expand outward. Okay, we measure that with lasers. The type of gas output that we see at the fumaroles around the edge, or coming out the top if it has steam vents at the top. How hot it is. There are some satellites that are specifically dedicated to monitoring high-profile volcanoes through infrared so that we can make sure that if there's even so much as half a degree increase, that might be enough to trigger a lahar. So we got to watch things that closely, right? So there's all sorts of infrastructure in place to watch these things, but there's always some that slip through the cracks. I think I told you last time about that volcano, that seamount off of Tonga that erupted, caught everyone totally off guard a couple years back. That sort of thing still happens every now and then. But we use the best knowledge and infrastructure we have to work on that to try and watch these things. Okay. Any questions?
So, you know those like little mini earthquakes that have been happening like in Texas since, I don't know, like the last couple summers?
Yes.
What are those results of them? Like, do we have any volcanoes in Texas?
We do, but none that are active.
Imagine, dude, Texans are too like stubborn to actually run.
Yeah. Yeah. No, so the earthquakes that we have around here, I haven't taught you much about earthquakes yet. For now, I'll just give you the cliff notes. An earthquake occurs where there is a buildup of stress along a fault plane. A fault plane is a crack in the ground. That crack occurred because of some tectonic stress that made it. The stress continues to build up along that crack until an earthquake occurs because of tectonic stress. There is nothing humanity can do to create a fault or to cause the buildup of stress along a fault plane. Positive. Because we're talking about nuclear bombs worth of energy here.
You have too much faith.
A nuclear bomb is not capable of doing that. I'm just talking about equivalence of energy. You should do
Tell me how much money you make off that.
yeah.
Probably none.
You should do a motivational speaking circuit. If you believe in yourself enough, you can make a fault. You can cause a fault. No. No. What we have been doing, the data seems to suggest that our oil-filled activities of injecting fluids into the ground, that includes
It's called a fracking, hydrofrack.
fracking, hydraulic fracture mining, yes. That injects liquid, but I'm not just talking about that. I'm also talking about collecting carbon dioxide out of the atmosphere to try and improve the climate. You know where we put that carbon dioxide? Back underground.
So we're adding pressure.
Right. We are adding fluids, which, yes, can't do increase pressure, but the fluids themselves reduce the friction on the fault planes, which causes them to slip. Again, we are not creating the stress. The tectonics are doing that. We are adding the friction reducing ingredient that causes them to slip earlier than they would have. So I'm choosing my words carefully here because it's not like everyone should just rat on the oil industry. The oil industry has contributed, but so has the attempt to fix climate change by taking carbon dioxide and putting it underground, right? This is what the data seems to suggest. There's a lot more data coming out about this, including a bunch more this year. I'm partnered with Lawrence Livermore National Laboratory. They are doing a whole bunch of seismic studies in the area. They are getting me their information when they collect it, and I have public seminars on this a couple times a year. The last one was back in October, okay, where I educate the public about how all of this works. I'm hoping to have the next one in about April. We're meeting in 4 days on Tuesday to Monday. Is that Monday the 26th? We're meeting on Monday the 26th to discuss when my next event is going to be. But that's where I share all this information, and I bring all sorts of important people in to discuss this with the public and answer their questions about it. Okay, so that's it in a nutshell. We are not making the earthquakes happen because we are not generating the force required to do so, but we are causing them to occur earlier than they would be.
Yeah, I was just curious because I remember like those little earthquakes. They even said that I think at least one has happened since I moved here.
Oh, we have several every day.
Oh,
Yeah.
cute.
Most of them are too small for you to notice.
Cute. I was just curious because you said that that's how we monitor the volcanoes. I'm like, I didn't think there was any in Texas.
No, so you absolutely can have earthquakes without volcanoes. It's just that one way that we monitor volcanoes is through earthquakes that occur around them. What was your thing?
I'm so confused. I thought the whole fracking thing was causing us to have an earthquake.
That's part of it.
Because I thought we never had any before.
Oh, we definitely did.
We did?
Oh, yes. Most people don't, which is why I'm having these public education seminars. Because right now, our community is very divided between, hey, oil industry, we need them because, you know, they support our entire economic basis here. The United States needs us because we provide half of the oil to the entire country. But then there's the other half that's like, yeah, but it's causing earthquakes and it's hurting the climate. And it's not just zeros and ones, right? It's not as easy as yes or no. It's way more complicated. And the only solution to that is everyone figuring out how to reduce impact while improving production,
Oh, okay.
right? Both things have to happen for us to keep up with the demand and responsibility of preserving our environment. So, yeah, no worries. You guys know I love questions. All right, so just really quick, I'm going to give you an intro to your Igneous Rocks lab, okay? Lab 2. Okay, so all of these things are things that you've learned about the last 2 lectures, so I'm just going to breeze through them. Your igneous textures, okay? So this PowerPoint you can find on Blackboard. It just gives you a quick rundown of things like texture and composition and things like that, okay? Your igneous textures, aphanitic, fine-grained, right? Too small to see with the naked eye. Might be vesicular. That would be an additional notation to make, okay? Phaneritic, large crystals, easy to see with the naked eye, okay? Porphyritic, combination of both. Then you've got glassy, pyroclastic, pegmatite, all of which the definitions are in the lecture 3 PowerPoint. So basically, it's going to run something like this. Variations on this theme. The same sort of format that you would answer in Lab 1, except now you're doing it with rocks instead of minerals. Okay. Does it have any quartz? Does it have any feldspar? What's the percentage of dark, aka ferromagnesian minerals that are in it, right? Things like that. I'm not guaranteeing it's going to look like this. I'm just telling you these are the sort of observations you'll need to make. Okay? So Lab 2, you'll go in there. You only have 12 samples. Each lab will only have 12 from now on. Lab 1 is the only one with 24, and that's because minerals make rocks. So you need to be more familiar with the minerals in quantity than the rocks. But it's going to run exactly the same as Lab 1, same format and everything. Any questions? That's not a question.
You know how many class periods I've been wanting to say that?
Isn't this your first class period of the day?
I mean, consecutive.
Okay. She means she's been wanting to say it for the last hour and 40 minutes.
Yeah.
All right. No questions? I'm going to end this here then.